There is a category of engineering failure that nobody talks about because it doesn't fit neatly into the stories that the industry prefers to tell about itself. It isn't the failure of a machine that was badly designed or carelessly built. It isn't the failure of an idea that was wrong from the beginning. It is something more uncomfortable than either of those things. It is the failure that happens when a machine is exactly as good as its creators intended, when it performs precisely as designed, when every specification is met and every calculation is validated, and the result is still catastrophic, not because the machine failed, but because the world the machine was built to run in was not capable of containing what it had created. This is the story of a locomotive that was, by every objective technical measure, one of the most impressive machines ever built for railway service. A locomotive that shattered speed records, exceeded every power output target, and demonstrated engineering capabilities that left observers genuinely astonished. And a locomotive that, in the process of doing all of those things exactly as intended, cracked bridges, buckled track, collapsed underpasses, and proved beyond any argument that the railway it had been designed to serve was simply not strong enough to survive the machine built to run on it. The story begins in Pennsylvania in 1919, in the aftermath of a war that had transformed American industry in ways that were still being fully understood. The railroads had been pushed to their limits during the conflict, hauling volumes of freight and numbers of troops that their infrastructure had never been designed to accommodate. The experience had revealed with brutal clarity exactly where the American railway system was strong and exactly where it was inadequate. And the Pennsylvania Railroad, one of the largest and most prestigious railway companies in the world, had come away from the war years with a conviction that defined its engineering program for the following decade. The railroad needed power, more power than anything currently running on its tracks. Power on a scale that would make the wartime demands look manageable, that would allow the company to haul heavier trains faster across a network that was already beginning to strain under the demands placed on it. The man tasked with delivering that power was a locomotive engineer named Harold Warwick Pierce, a meticulous and somewhat obsessive designer who had spent 20 years studying the relationship between locomotive performance and track infrastructure, with an attention to detail that his colleagues found either admirable or exhausting, depending on how closely they had to work with him. Pierce understood something that many locomotive designers of his era preferred not to think about too carefully. A locomotive does not exist in isolation. It exists in a relationship with the track beneath it, the bridges it crosses, the curves it navigates, and the gradients it climbs. The power that a locomotive can safely deliver is not simply a function of what its boiler and cylinders can produce. It is a function of what the world beneath its wheels can absorb. Pierce had written about this relationship in papers that received respectful attention from his peers and were then largely ignored, because the practical demands of railway operation did not leave much room for the kind of systemic thinking that his work required. Railway companies needed locomotives that could move trains. They needed them quickly, and they needed them cheaply. The question of whether the infrastructure could handle what the locomotives would deliver was, in the culture of American railway engineering in the early 20th century, somebody else's problem. Usually, the infrastructure department's problem, usually addressed after the fact, usually expensively. What happened when Pierce was given the assignment to develop the next generation of Pennsylvania Railroad power is one of the more ironic episodes in railway history. The man who had spent his career warning about the relationship between locomotive power and infrastructure capacity was handed a mandate to maximize locomotive power with almost no constraints on what that maximization might mean for the power. Infrastructure. The railroad's management had looked at the numbers from the war years and concluded that the primary limiting factor on their operational capacity was locomotive power. They wanted more. They wanted significantly more, and they wanted Pierce to provide it. Pierce's response to this mandate was the design that he designated internally as the Class X. A locomotive of such ambition and such carefully calculated engineering that the drawings alone filled several large cabinets in the Pennsylvania Railroad's engineering department. The wheel arrangement was 2120, 12 coupled driving wheels in a single group, the largest number of coupled wheels ever specified for a locomotive intended for main-line freight service in America. The boiler was designed to operate at pressures that were at the upper limit of what contemporary boiler manufacturing could safely produce. The cylinders were sized to extract the maximum possible tractive effort from that pressure. Every dimension was calculated to produce the highest achievable power output within the physical envelope that the Pennsylvania Railroad's loading gauge permitted. The tractive effort figure that Pierce arrived at was extraordinary. The Class X, on paper, was capable of producing a starting tractive effort that exceeded anything previously attempted in American railway practice. The theoretical ability to start and move a train of freight cars from rest was so far beyond existing designs that when Pierce presented the figures to the railroad's engineering committee, there was a moment of silence before anyone spoke. Then the committee chairman, a veteran railway engineer named Thomas Aldrich, who had been building and operating locomotives for 30 years, asked a single question. He asked whether Pierce had calculated the forces that would be transmitted to the track and bridges during normal operation. Pierce had calculated them. He had, in fact, calculated them with great precision and placed those calculations in the appendix of his presentation document, where they sat in careful columns of figures that represented, for anyone who read them with attention, a detailed prediction of exactly what was going to happen when the Class X met the Pennsylvania Railroad's infrastructure at speed. The forces were, in the language of engineering specification, challenging. In the language of plain description, they were alarming. Pierce had done his job. He had warned the committee. He had put the numbers in the appendix where anyone who wanted to find them could find them. The committee approved the design anyway. The first Class X was completed at the Altoona Works of the Pennsylvania Railroad in 1921, and from the moment it rolled out of the erecting shop, it was clear that something genuinely unusual had been built. The locomotive was massive in a way that photographs of the period struggle to convey, because the cameras of the era tended to flatten the perspective and reduce the impression of scale. Visitors to the works who stood beside it for the first time uniformly reported the same reaction. The machine was bigger than they had expected, not just larger than other locomotives they had seen, but larger in a way that seemed to push against some intuitive sense of what a railway locomotive should be allowed to be. The mechanical finish was impeccable, as Pennsylvania Railroad locomotives always were. The boiler cladding was smooth and precise. The valve gear was adjusted with the exacting standards that Pierce demanded. The paintwork, that characteristic Pennsylvania Railroad Tuscan red, was applied with the care appropriate to a machine that represented the railroad's highest engineering achievement. Works number 5550 left. Altoona, looking like what it was, the product of 20 years of careful thinking about locomotive power, translated into physical reality by some of the finest craftsmen in American manufacturing. The initial trials were conducted on a test track at Altoona under controlled conditions, and they were spectacular. The performance data that came back from those tests exceeded even Pierce's confident predictions. The boiler steamed freely at pressures that other designs struggled to sustain. The valve gear delivered steam to the cylinders with an efficiency that translated directly into tractive effort figures on the dynamometer car. The fuel consumption was higher than conventional designs, as was inevitable given the power output, but within the range that the railroad had accepted as the cost of the performance it was buying. What the Altoona test track could not reveal, and what Pierce's appendix calculations had predicted with uncomfortable precision, was what would happen when the Class X met the actual Pennsylvania Railroad main line at the speeds and loads for which it had been designed. The first revenue service trial was organized on a section of the Pittsburgh Division, one of the most demanding freight routes on the Pennsylvania Railroad system, a line that combined significant grades with the kind of heavy train weights that justified the enormous power output that the Class X had been built to provide. The locomotive was assigned a train of loaded coal hoppers that represented about as severe a test as the route could offer. A team of engineers rode in an observation car attached to the rear of the train, monitoring performance instruments and recording everything that happened. What happened in the first hour of that trial run would have been, to anyone reading Pierce's appendix, entirely predictable. The Class X performed magnificently in terms of its own mechanical function. It accelerated the heavy train with a willingness that astonished the footplate crew, men who had spent careers operating the best motive power that American railway practice could produce. It sustained speeds up the grades that the route demanded at levels that no previous locomotive had approached with a comparable train. The dynamometer readings were everything the specification had promised. But underneath the locomotive and in the bridges that it crossed, things were happening that had nothing to do with the locomotive's own mechanical performance and everything to do with the forces that Pierce's appendix had calculated. The track, standard Pennsylvania Railroad mainline construction that was adequate for every other locomotive in the fleet, was experiencing forces that it was not designed to handle. The 12 coupled driving wheels, transmitting tractive effort to the rails with a force that no previous design had approached, were generating dynamic loads at speed that exceeded the track structure's designed capacity at several points along the route. The evidence was not immediately dramatic. There was no derailment, no catastrophic failure, no event that would have stopped the trial in its tracks. What there was instead was a series of small but significant anomalies: a rail joint displaced slightly further than normal, a bridge timber that showed stress marks not present before the locomotive crossed, a section of ballast redistributed by the passage of forces that it had not been designed to accommodate. Each individual anomaly was small enough to be noted and then rationalized as within acceptable limits. The cumulative pattern, had anyone been looking at all the anomalies together rather than each in isolation, told a very different story. The trial was declared a success. The Class X had performed as designed. The locomotive was placed into regular service. The infrastructure problems announced themselves over the following months with a persistence that became impossible to ignore. Track geometry deteriorated on the sections where the Class X operated at rates that the maintenance department had never seen. Bridge inspections revealed stress patterns that structural engineers flagged as requiring attention with an urgency that was unusual in a system where bridges were expected to last decades between major interventions. The ballast sections that carried the heaviest Class X traffic required restoring on maintenance intervals that were half those required by every other section of comparable track. The maintenance department began keeping records specifically related to Class X operations, and those records, as they accumulated through 1922 and into 1923, painted a picture that was becoming impossible to dismiss. The locomotive was not damaging the infrastructure in any single dramatic incident. It was wearing it out, grinding it down through the accumulated effect of forces that were simply beyond what the structures had been built to sustain. Every crossing, every bridge, every rail joint, every bed of ballast on the routes where the Class X operated was aging faster than it should, and the aging was directly and demonstrably correlated with the passage of the locomotive. Pierce, when the maintenance records were presented to him, said nothing that he had not already said in the appendix to his original design presentation. he had calculated these forces. He had put the numbers in the document. The committee had approved the design anyway. What he said to the engineering committee when the infrastructure reports began arriving was measured and precise and absolutely accurate. He said that the solution was not to modify the locomotive, but to upgrade the infrastructure, that the figures in the appendix had specified what would be required, and that the railroad had always had the option of making those upgrades before placing the locomotive in service. The infrastructure upgrades that were required to allow the Class X to operate without destroying the track beneath it were estimated when a proper engineering assessment was finally commissioned in 1923 at a figure that made the railroad's financial officers physically uncomfortable. The calculation covered heavier rail sections on the main freight routes, bridge strengthening across more than 40 structures, drainage improvements to reduce the dynamic loading effects of soft subgrade, and ballast upgrades across hundreds of miles of route. The total was a number with enough zeros in it to ensure that the conversation immediately became political rather than technical. The political decision that followed was shaped by a context that Pierce found maddening. The railroad had invested substantially in the construction and operation of the Class X fleet, which by 1923 included 4 examples. It had committed to operating them on specific routes where their power output justified the investment. Acknowledging that the infrastructure was inadequate meant acknowledging that the design approval had been premature, that the appendix calculations should have triggered infrastructure upgrades before the locomotives entered service, and that the railroad's management had effectively made a decision that cost considerably more to correct than it would have cost to prevent. Nobody in the Pennsylvania Railroad's management structure was eager to sign their name to that acknowledgement. Instead, a series of operational restrictions were imposed on the Class X fleet. Speed restrictions on specific bridges and track sections. Load restrictions that reduced the train weights of the locomotives were permitted to haul. Route restrictions that kept the Class X off the most vulnerable sections of the network entirely. Each restriction was presented as a temporary measure while infrastructure work was completed. In reality, the infrastructure work was never fully completed because the full program of upgrades was never fully funded. What emerged from this process was a locomotive that was, in operational terms, a paradox. It had been built specifically to haul heavier trains faster than any previous design. The restrictions imposed to protect the infrastructure meant that it regularly operated below its design capacity, hauling lighter trains at lower speeds than its power output could have supported. The most powerful freight locomotive in Pennsylvania Railroad history spent its service life deliberately throttled back, constrained by the inadequacy of the world it had been built to run in. The irony was not lost on Pierce, who continued to work for the railroad and continued to write papers about the relationship between locomotive power and infrastructure capacity, papers that were now read with somewhat more attention than they had previously received. He never said publicly what he had said privately to colleagues who were close enough to him to hear the unguarded version that the Class X was not a failure of locomotive engineering. It was a failure of organizational decision-making. The locomotive had done exactly what it was designed to do. The railroad had declined to do what was necessary to accommodate the locomotive it had commissioned. The Class X fleet was gradually restricted to an increasingly small number of routes where the infrastructure could handle their operation without unacceptable maintenance consequences. By 1930, with the Depression reducing freight volumes and with the ongoing infrastructure costs of Class X operations increasingly difficult to justify, the decision was made to withdraw the fleet from service. The 4 locomotives were placed in storage at Altoona, where they sat through the 1930s as the railroad's financial position deteriorated, and the question of what to do with them was repeatedly deferred in favor of more urgent priorities. The war years brought a brief revival. The same demands that had originally motivated the Class X program, the need to move enormous volumes of freight quickly across a network under strain, created a temptation to return the stored locomotives to service. 2 of the 4 were inspected and assessed as capable of being returned to operational condition with acceptable maintenance investment. They were returned to service in 1942 and worked through the war years on carefully selected routes where the infrastructure could handle them, hauling war material with the effortless power that had always been their defining characteristic. After the war, with the railroad again consolidating its operations and planning for a future that everyone in the industry understood would eventually belong to diesel traction, the Class X question was resolved with quiet finality. The 2 locomotives returned from war service were assessed and found to require boiler work that the railroad decided not to fund. All 4 examples were officially withdrawn from service in 1947 and scrapped in 1948, with a thoroughness that was characteristic of the period. No examples were preserved. The design drawings survived in the railroad's archives, along with Pierce's original presentation document and the appendix that had predicted in careful columns of figures exactly what was going to happen. Pierce himself retired from the Pennsylvania Railroad in 1944 after 25 years of service following the Class X program. He spent his retirement writing the book that he had been accumulating material for throughout his working life, a comprehensive study of the relationship between locomotive design and infrastructure capacity that drew on every case study he had encountered during his career, and used the Class X program as its central and most extensively documented example. The book was published in 1951 and received the kind of reception that genuinely useful technical books often receive, which is to say that it was reviewed respectfully, purchased in modest quantities by engineering libraries and thoughtful practitioners, and then gradually became the quiet reference that experienced engineers recommended to younger colleagues who were beginning to understand that the problems it described were not historical curiosities, but permanent features of the landscape they were working in. Pierce died in 1956, 5 years after the book's publication and 8 years after the last Class X was scrapped. He never saw the design drawings reproduced in a historical publication or the Class X discussed as anything other than a footnote in the Pennsylvania Railroad's operational history. His name does not appear in the popular histories of American locomotive engineering that were published in the decades following his death. The book is still occasionally cited in academic literature on railway infrastructure management. What remains of the Class X story is entirely documentary. The design drawings in the Pennsylvania Railroad's archive, now held by various historical collections. The maintenance records that told the story of what happened to the infrastructure, Pierce's presentation document with the appendix that predicted everything, and the book which translated a specific experience into general principles that were applicable to every situation where engineering, ambition, and infrastructure reality met and found themselves incompatible. The locomotive that destroyed every railway that tried to run it was not a monster or a mistake. It was a brilliant machine built by a brilliant engineer who understood exactly what he was building and exactly what it would require, and who put that understanding in an appendix where everyone who needed to act on it could find it, and most of them chose not to look. The Class X teaches an engineering lesson that the industry has learnt and forgotten and learnt again across the century, and more since Pierce put his calculations on paper. The lesson is that a machine does not exist in isolation. It exists in relationship with the world that must support it, and when the machine is more capable than the world is prepared to accommodate, the world does not expand to receive it. It cracks and buckles and wears, and eventually the machine is restricted or retired, and the infrastructure is left bearing the costs of an ambition that it was never asked whether it could sustain. The most powerful locomotive in Pennsylvania railroad history destroyed the tracks beneath it, not because it was badly built or badly designed. It destroyed them because it was exactly as good as it was supposed to be in a world that had not been made ready for what exactly that good would mean. Pierce knew. He wrote it in the appendix. The committee approved the design anyway, and the locomotive ran, and the bridges cracked, and the rails buckled, and the maintenance records filled with numbers that told a story that nobody wanted to be the one to read out loud. Until the locomotives were scrapped, and the records were filed, and the story became an appendix to an appendix, waiting for anyone patient enough to look for it.